All right. Section 1.5 is inverse function. Every time we learn a new thing in math, we turn right around and learn to undo it. And the undoing of functions is inverse functions. All right. Tell me anything you remember about inverse functions. Let's get some notes. What do you remember?
Team.
Okay, so you remember that trig functions have inverse functions.
Yes.
And they make you shiver.
Yes.
Okay, I understand. Me too. Me too. I'm talking about in general, what are some of the properties of inverse functions? You remember
I
one?
just remember like it would give you like a thing in an order pair and it would be the radian answer. Like it might be the square root of 3 over like sine square root of 3 over 2, and then it would have to be negative pi over 2 or pi over 2 in between that.
Okay. You're still talking specifically about inverse trig functions. I'm talking about in general, what does it mean to be inverse function? Madison, what do you remember? Oh, I love that. That's a good thing. You can only take the inverse. Zoom in just a little bit. Take the inverse, or you know what? I should say find. You're not really taking the inverse, you're finding an inverse. You can only find the inverse of one-to-one functions. A squaring machine. And I'll let you tell me another one. A squaring machine. You know, why is y equals x squared not 1-to-1?
Because it
For some x's, no, excuse me, for some y's come from 2 different x's. Remember? Oh, in grading your homework last night, those problems, those comprehension questions at the beginning of the chapter, I really want to see you putting into your own words what some of these terms mean. And number 1, I graded it last night. Some of you got credit for it, some of you got half credit for it. But remember, some of you wrote a relation is an ordered pair. No, it's a set of ordered pairs. And then some of you used very vague language in defining a function. A function is an ordered pair for which each x only corresponds to one y. I think someone said the x's do not repeat. Oh, that's not technically true. They can repeat, but every time you put in the same x, you get out the same y. They can't repeat with different y values. That's a function. And then a 1-to-1 function, not only for each x is there only one y, but also for each y there's only one x. Now, how can you tell by looking at a graph that it's a 1-to-1 function? The horizontal line test. So if you think about the graph of y equals x squared, that's certainly not 1-to-1. Whatever this x is, this different x gives you the same y. That's counted by 4s, I guess, here. That's not 1-to-1. That's 2 different x's giving you the same y. And the reason we can't find the inverse function of a function that's not 1-to-1 is, remember what an inverse function does. A function is like a machine. You put a number into, the machine does whatever it's supposed to do and spits out an answer. So for a squaring machine, you put in a 2, it spits out a 4. The inverse machine is supposed to take that 4 and be able to tell you what number you originally put into the squaring machine. Well, when you put that 4 in the square rooting machine, the calculus machine starts smoking and says, I don't know if you put in a +2 or a -2, because both of them would have given you a 4. So that's why you can't find an undoing function for a function that's not 1-to-1. That inverse function is going, I can't tell what you put into the original because this function is not 1-to-1. All right, so that's an important thing you remember. Rachel, did you remember something different about inverse functions? Yes, yes, you absolutely do. I'm not gonna try to write that one down because we're actually gonna do an example like that, but that is the process. You're absolutely right. What other fact do you remember about a function and its inverse? Huge difference between the inverse of a function and the reciprocal of a function. The reciprocal of x squared is what? 1 over x squared. The inverse function of x squared, well, you can't even find it if you're looking at the entire domain of the function. If we restrict the domain to only positive x's, then we could find the inverse, but it wouldn't be 1 over x squared, it'd be the square root of x. So inverse and reciprocal don't mean the same. What else? Remember anything about the graph of a function and its inverse?
I mean,
So y equals x. Good. The graph of a function and its inverse are reflections of each other. WRT stands for let me try one more time. WRT stands for with respect to the identity function, y equals x. For example, if you graph y equals x cubed, is that a one-to-one function? Yes, so you can find its inverse. Yes, what would be the inverse of the cubing function? The cube rooting function. If you put a 2 into the cubing function, you get out an 8. If you put an 8 into the cube root function, it has no problem telling you what you must have put into the original machine that would have put out an 8. It's got to be a 2. -2 cube wouldn't have given you 8. It would have given you -8. So if you think about the graph of, let me do it in a different color. If you think of the graph of you might do a better job of that than I did. But y equals cube root of x. We've always said x cubed looks like a vertical snake. Cube root of x looks like a horizontal snake. And then, just have to use a highlighter for this. This is the line y equals x. You know how hard, those of you who know me, know how difficult it is for me to flip something in my head. Honestly, if I didn't know what x cubed looked like, I would not, I don't know why my brain works this way, but I wouldn't be able to take that and just flip it diagonally. I can flip something horizontally, I can flip it vertically, I can't flip it diagonally, but I just happen to know what y equals cube root of x looks like. Now, actually, when I graph a function and its inverse, making a set of ordered pairs helps me. I make the XY table, and what do you know about the ordered pairs for a function and its inverse? They're reversed. Let me think of the best way to write it so you don't have to erase. for the function. Oh, I got it. If f of x has ordered pair A, B, then what symbol did we use? We could say g of x is its inverse, but if I want to stick with f of x, what symbol did we use to indicate we were talking about the inverse function? It looks like the exponent -1, but I've got to keep very clear in my head that when I write this, I'm talking about the reciprocal of a variable. When I write a function, that's not talking about the reciprocal of f, that's talking about the inverse of f. So it's one time that I think maybe mathematicians could have been reciprocal, could have been a bit better with their notation. I don't like one symbol that can mean two different things depending on how you're using it, but that's the way it is. So I can say if f has the ordered pair AB, then f inverse has the ordered pair, I'll just shorten this, say BA. And that's how I actually graph inverse functions, because I can't flip things diagonally in my head. I have to take a few ordered pairs from the function and reverse them, plot those ordered pairs, and then I can see how to connect them to make it be the reflection of the original function with respect to y equals x. All right, that's some good things to remember about inverse functions. I was going to pull this up. Sometimes I just get so intent on making sure I explain things so thoroughly that we don't finish our notes. So I think that's happened every day since we started. So instead of opening the book and reading these 3 pages to you, it may be a good idea for you to open the book. This is the summary of what's on those 3 pages. And then there's a box that has some exploration problems, like, can you figure out what the inverse of this function is without having to go through a process? If f of x is 2x, what do you think its inverse? If f of x is a doubling function, what would its inverse be? A halving function. And if f of x was a doubling and adding 3 function, what would the inverse function have to do? You would actually, you got to do it in the reverse order. You got to subtract 3 first and then take a half. And you know, oh, I thought of one other note. If I have enough room, I'm going to put one more dot up here. One more thing we know about inverse functions is if we put f of x into the inverse function, that's our notation for a composite function, isn't it? We take the function f of x and put it into the inverse function. What should we always get at? They should undo each other and give us back the original x. So if we put an x value into the function f, we take that answer and put it into the inverse, we should get back out the same x that we originally put in. All right, that's a summary of what's on these pages, and as much as I like to read to you, you have to read it yourself. It also explains well, the dot that I just put the function put into the inverse function undo each other and just give you x really tells you how to do this problem. This says show that f and g are inverse functions algebraically. And then, of course, we can do it graphically just by graphing both of them and making sure that they look like reflections of each other along the line y equals x. But how do we show that algebraically? And think about the dot I just wrote. Form the two composite functions. Show that if you put f of x into the inverse, they undo each other and just give you x. And then we know from the day we talked about composite functions usually are not equivalent. F circle G is not the same as G circle F. Well, with inverse functions, both things have to be true. So I guess I'll say, and if I put the inverse function into the function itself, that will also just give me f. Both composite functions have to give me plain old x, and then I can say, yes, those two functions are inverses of each other. That's what we're going to use to show in number 16 that these are inverses of each other algebraically. So I'm going to find f of g of x, see what that is, and then I'm going to find g of f of x and show that both of them give me x. All right. G of f or f of g of x means take g of x and put it into f. Well, what is g of x?
What is it?
It's this guy. So that's what I need to put in place of all the x's in the function f. F of 1 minus x over x. That's the expression that I'm going to put in place of this x right here. 1 over 1 plus whatever g of x was. Now you're going to have to bring back, and I realize they may be rusty now, perfectly reasonable after you haven't looked at algebra and trig for 3 months, that it would be rusty and you have to work to bring it back. But one of the skills you have to bring back is cleaning up complex fractions. You're never going to leave a baby fraction within a big fraction as your answer. So whose paper was it? Brie, I think it was yours. You wrote multiply by the baby denominator. And then I know who you had for math. If you call it baby denominator, that's how we clean up complex fractions. What is the baby denominator? X. So I multiply the whole fraction by x over x. And since that denominator has 2 terms, I have to make sure I multiply it by both terms. So the big numerator just becomes what? 1 times x is x. The denominator, I'm going to say x times 1 is x. What's x times this fraction? Yeah, that's why you multiply by x so that they would divide out in that second term. So x plus 1 minus x. You don't need those parentheses because you're adding, but if it helps your eyeball, write it. Or if it will keep you from making a mistake when it's subtraction, just go ahead and put it there. It doesn't hurt to have those parentheses. What does that clean up to be? X over one, and what is X over one? X. And we've only half proven that those two functions are inverses of each other. What else do we have to do to prove they're inverse?
Plug it in.
The other composite function, find G circle F of X. That means take F of X and put it into G. And that means take whatever F of X is, in this case, 1 over 1 plus X, and put it in place of both of those X's in function G. Let me be quiet for just a minute and see how far you can get in cleaning up that resulting complex fraction. I'm gonna hide my work, let you work a minute, and then we'll see if we get the same thing. You know what you should get if these two functions are inverses of each other? What should you get? Just X. Here's the inverse function when I formed it, or not import, the composite function when I formed it and before I cleaned it up. Is that what you had? Okay. How do you clean that up? The baby denominator is 1 plus X. So multiply the whole fraction by 1 plus X over 1 plus X, because the only thing you can really multiply by something without changing it is 1. It has to be 1 that you're multiplying by, something over itself. Now distribute that through the numerator, and what did you get? 1 plus X, and you don't have to have those parentheses, but they help my eyeballs, minus 1. And in the denominator, just get 1. And then sure enough, that does exactly what it's supposed to do. And it makes Abigail. Yes!
They were cheering.
Huh?
They were cheering for us.
Oh, they did clap right at the same. Yes, good for you. Oh.
It's like,
All right. I have to contact the help desk folks. So many issues with computers that they've taken away our ability to download a program on the computer. They're the only ones that can download stuff because people are downloading stuff they shouldn't be downloading. But I need my TI-84 put back on here. If I had it put back on here, they wipe it out every semester. We would do this B part. We would graph this and graph this, and I would also graph the line y equals x so that I could see. Sure enough, this looks like a reflection of that. Now, what you have to be aware of is both of these had restricted domains. Without restricted domains, they probably wouldn't look like reflections of each other over their whole domain. So if I was, one of you can do this for me and No, you type it in and I'll lay it up here. Graph for the B part, graph f of x, g of x, and y equals x in the window. You only want your x's go greater than 0 here and between 0 and 1 here. So I really only want to look at x's between, I'll go ahead and, yeah, 0 and 1. I'll look at that part of the graph. From x's go from 0 to 1, and my y's, how am I going to figure out what my y's need to go to?
When they just x greater than there, just stop them at 1, 2.
I want to look at that part of the graph and then I'll zoom out. But to figure out what to set my y's to, let's see, if I let x be 0, what would I get in this function? 1. And if I let x be 1, what would I get in this function? A half. Here I'd get, if x is 0, I'd get 1. If x was 1, I'd get 0. So I'm just going to let my y's go from, what do we say, a half. I'm going to do them also from 0 to 1, just because I think that'll be good enough picture, even though I might have to zoom out some more. I'm just guessing what window to use. The last thing I need to tell the calculator is what I want my tick marks to count by. That's x scale. I'm going to make it count by a half, since I know that if I let x be 1 here, I'm going to get a half, and might as well let y scale be a half too. I'm kind of guessing at what best window to use, and then I can change the window if I need to. Now, I've even been able to show you the graphing calculator. Most of you've seen them and you're okay with them. Make sure when you type this in, you have binomials in parentheses, because your calculators won't perform to do the order of operations. If you type 1 divided by 1 x, what's the calculator going to do first? It's going to say 1 divided by 1 is 1, and it's going to graph 1 plus x, which is a line. You have to have that in parentheses for the calculator to know, oh, you mean 1 over the whole 1 plus x. The other thing you have to watch out for, no, not watch out for, but the other thing that I'll show you the minute I get my calculator back on my computer is where to type all this in and change x scale, y scale. We'll have a computer day. I need to get that fixed today. Madison, do you have it all typed in, or does anyone have it? Do you have it? I say, just here it is. Okay, let me show you. What Isaiah did was type y equals and type in those 3 functions, f of x, g of x, and y equals x. And then this second button is window. That's where you say, I want my x's to go from 0 to 1, counting by half. And I want my y's to go from 0 to 1, counting by a half. That's what that is. You don't really have to worry about that. But here's my shorthand notation for exactly, here's what it looks like on the computer.
You make your equations into like the actual way it's written.
Version of PI 84 you have. I said it's not pretty close to probably the latest version, and it's actually practice. Unless I get an update, my computer won't look like mine will look like. Yeah, so don't worry about it. It doesn't affect anything. It just looks prettier when the computer makes it look like it does on your paper. And then when Isaiah hit graph, even some P84s let you graph in different colors. Maybe the f of x is in blue and g of x is in red, and sure enough, you can see here's the line y equals x. Let me have that blue and red. I can see that this one is the reflection of this one about that one. So in a problem like this on the homework, the B part, do what we just did, type in both functions and the identity line, and then rough sketch that on your paper. You know, just make a little XY axis and go whoop, whoop, whoop. And if it looks like one's the reflection of the other. As I said to Madison today, our goal in graphing or in knowing our graphs this semester is not so that we can give a whole lot of, or say intimate, that's not the right word, a whole lot of precise detail. It's so that we have a quick mental image in our head before we pick up the calculator. So that if we graph something and we forgot to use those all important parentheses, if I think I've graphed f of x and my calculator just gives me a line, I'm supposed to be smart enough to go, whoa, that's not a linear equation. What's going on? Let me figure out what's going on. All right. So, what I really hope to finish today was this front page. And if we get beyond that, yay, but we get through the front page, that'll be good. So now you remember how to show that two functions are inverses of each other. What if I just give you one function and ask you to find the inverse function? And that's what Rachel was remembering from pre-calculus. There's two things you need to do. Doesn't matter in what order you do them. I think our pre-calculus book now does it differently than our previous pre-calculus book. But you can either, well, change that to y. That's the same thing with y. You can either solve for x and then interchange the variables, or you can interchange the variables first and then solve for y. Doesn't matter which order you do those two things. But I want to, I really don't remember which this pre-calculus book does. If I put y equals 3/5 root of 2x minus 1, I think I'll solve for x and then interchange the variable, because you want your inverse function to be in terms of x instead of in terms of y. Let's figure it out, and your powers of holding things in your head may be better than mine, but you may be able to say, okay, I built a machine that doubles any x I put in. Those are my asks, that helps. Doubles any x I put in, then it subtracts 1, and then it takes the 5th root, and then it multiplies, and then it triples. Can you do that backwards? Instead of tripling at last, I'm going to do what first? I'm going to divide by 3. And then, instead of taking the 5th root, I'm going to 5th power. And then, instead of subtracting 1, I'm going to add 1. And then, instead of doubling, I'm going to divide. And if you can write that down, if you can figure that out and write it down, that's okay. Hey, maybe you can, I cannot. So I'm going to show my steps here to make sure I get this right. Solving for x. Solve that for x. First, I would divide by 3. both sides by 3. And that's what you told me when we all had our eyes closed trying to squint this out. And after I divide it by 3, how do I undo 5th root? 5th power. Raise both sides to the 5th power. I may want to clean up that left-hand side a little bit before I continue. I can either clean it up now or clean it up later. It's gonna have to be cleaned up at some point. I'm gonna go ahead and say that's y to the 5th over 243. 39, 27, 81, 243, that's right. What? I've been chewing stuff for a long time. Then what? Add 1 to both sides. You know, the way I'm writing this, some of you don't worry enough about how your paper looks. Some of you worry too much about how your paper looks. This is fine with me. I want you to work down the page, because if you work across, all of a sudden it looks like you have an equation with 3 sides, 4 sides, 5 sides. You're solving an equation. You need to go down so you can see your left and right hand side. But if you run out of room and want to go and now go here, that's fine. I wouldn't leave some of the stuff I've been fine with. And then there is a level where I'm not fine with it anymore. But that's okay. That's perfectly fine. I made a mistake, but because I'm working down the page, when I asked myself, is this equivalent to the line above it? I immediately went, oh, it's not. What did I do? Then I forgot to add my 1 to the left. It's not a benefit of working down the page. And then what? Divide by 2. Once again, it doesn't matter so much in what order you do things, but if I divide by 2 right here, I'm going to have a complex fraction. It's okay, I know how to clean up a complex fraction. Or I could go ahead and get a common denominator, make this a single fraction, and then divide by 2. Either one's okay, but I don't want to leave a complex fraction as my answer. So I'm going to think of that 1 as, how would I write it if I wanted a common denominator? 243 over 243, so that when I combine those 2 fractions, I have y to the 5th plus 243 over 243. The OCD person that I am, I look at this and go, if I split that into 2 terms, would it be equivalent to the left-hand side right here? Yeah, it would. So I'm confident. And then I can divide by 2 and not have a complex fraction. Dividing by 2 is the same as multiplying by a half. I can see if I multiply both sides by half, I have y to the 5th plus 243 over 486. Yeah, the same thing. The same thing. And then I want to interchange my variables, because if I left this as my answer and said this is my inverse function would be in terms of y. I don't want my inverse function in terms of y, I want it in terms of x. So I can write it as x to the 5th plus 243 over 486 equals y. Or I could use the inverse function notation. Since it said find f inverse, I'm going to use that notation and write it either as I'm showing, or as Rachel said, and either one's perfectly fine. You could separate that into two fractions and just have the x to the fifth over 486 plus a half. And that doesn't really sound like what we were coming up with in our head. When we were talking through finding the inverse, we didn't have a 486 in there. Because in our heads, we just said raise both sides to the fifth power. We didn't say what that was. We didn't get a common denominator. We talked through the process backwards, but we really didn't define it well until we used that process for finding the inverse function. The directions say find the function and its inverse. So, find the inverse and state the domain and the ranges of the two functions. What is the domain of f?
Oh,
That's the right hand, but that's not the domain.
anything that's greater than, that makes 2x minus 1 greater than
Yeah.
8.
So you can't take the fifth root of a negative? You can. Oh, you can. You can take odd roots of negatives.
Oh.
You take cube root of
Oh,
negative
yeah,
eight,
you can.
right? You can't take even roots of negative. So
So it's every.
yeah, you can let x be anything here. Because we can take odd roots of positive and odd roots of negative and odd roots of 0. The domain's negative infinity to infinity. What about our inverse function? Any number in the whole wide world, we can raise it to the fifth power and then evaluate that. So both domain and range are negative infinity to infinity. You have 7 minutes. Let me skip the next example for a minute. At least it's the same kind of problem. Number 62 says restrict the domain of the function f of x equals absolute value of x minus 3 to an infinite interval. How is restricted possibly infinite? Aren't those two like oxymorons?
Yep.
Huh?
Yeah, it's wrong.
Okay, let me think about it. What does that function look like? F of x equals absolute value of x minus 3. V shape, which turns around at the point 3, 0. It's the V shape, scooted 3 to the right. So there. We agree that currently our function is not 1-to-1 and therefore does not have an inverse. Yeah. How could I restrict it so that it would have an inverse?
That's
Either use the left-hand side would be 1-to-1, or the right-hand side would be 1-to-1. I could use one or the other. Technically, I could use from 7 to infinity. Would that be 1-to-1 if I just use x is 7 to infinity? Yeah, it just wouldn't be the biggest possible interval that I could use. Would it be an infinite interval? Okay, so that does make sense. I can just use the right-hand side and it would still be an infinite interval because it goes forever. Okay, so that makes sense.
oh.
That one was for me. So the domain of this is negative infinity to infinity, the original function. But I'm gonna use my highlighter here. I could either choose the left side or the right side. Choose the right side. And what if I included this point 3, 0? Would the function still be 1-to-1 if I included this point? Yeah, it would. So I'm going to include it. Say the restricted domain that I chose not that I had to, but the one I chose was from 3 to infinity, including the 3, but you can never really include infinity. All right. So restricted on which the interval is 1 to 1, find the inverse of the restricted function and give its domain. Okay, inverse of the restricted function. What is f of x is the absolute value of x minus 3, as long as you're putting in numbers that are at least 3. If you put in a 3, what do you get? 0. Put in a 4, what do you get? 1. Is that the same thing as if the absolute value wasn't there?
Yeah.
If you're putting in numbers that are bigger than 3, you don't need the absolute value because you're getting a positive anyway. So for x is greater than or equal to 3, f of x is just x minus 3. So you get the same thing whether you have the absolute value or not. Y equals x minus 3. Just add 3 to both sides and then interchange your variables. And you have the inverse function is x plus 3. If I put a 7 into this inverse function, what do I get? 4. If I put a 4 in, I said the wrong thing. I put a 7 into this function, I get out a 4. If I put that 4 in the inverse function, do I get out the same thing I originally put in here?
Yes.
Yes, I do. All right, there's only one other thing I want to say, two super fast. This one, there's one like it in the homework, and there's a curveball. I wish we had had time to do it. It's gonna make you squint in the homework, but you can email before my grade day, right?
8 hours.
Okay, no, way before 8 hours. All right, so figure that out. Yay. Other thing I wanted to say is just this real quick. If x's are less than 3, function is, wish we had time to discuss it, but you can see that that works if you plug in numbers. If you plug 2 into this and 2 into that, you'll get the same answer. Plug in 1 into this and 1 into that, you'll get the same answer. So if we had picked the left-hand side, we would have written the function as this and find the inverse. Because we chose the right-hand side, it was a little bit simpler. All right, y'all have a great day. Email me if you need me. If you email me, send me a picture of your work so I can. Yes, ma'am.
Where to find out after the email?
No, I'm gonna send you an email from my iPad tonight, and you let me know if you get it. Okay? I'm gonna make myself a note, send Madison an email.